Welcome to Scoli Sleep Stories. Before we begin, take a moment to get comfortable, let the day soften around you, and settle in for a calm documentary made for curious minds. If these stories help you rest, learn, or simply enjoy a quieter part of the day, please consider liking this episode and subscribing to the channel. Now, when you are ready, let us begin. Chapter 1: At the Mouth of the Cave. The path begins beneath an open evening sky. Soft light rests across the grass, giving each blade a muted shade of green. Along the edge of the path, fallen leaves lie in quiet layers. Some have only recently settled, while others are already becoming part of the soil. Their colors have softened into brown, gold, and deep red. A mild breeze passes through them, making the faintest rustle. Beyond the grass, pale limestone rises from the ground. Its weathered surfaces are rounded, with shallow grooves where rainwater has traveled. Small patches of moss rest in sheltered places, and slender roots follow the spaces between stone and earth. Nearby, a stream moves steadily through the landscape. It is not wide, and its voice is gentle. Water slips over pebbles, gathers in clear pools, and continues beneath overhanging grasses. For now, the stream remains beneath the open sky. Later we will see how water can disappear below ground and continue through passages hidden within the hills. Ahead, at the base of a low limestone slope, the cave entrance comes into view. It does not appear suddenly. The opening reveals itself little by little as the path curves between the trees. At first it is only a shaded place among pale rocks. Then its outline becomes clearer. It is a broad arch in the hillside, spacious enough to enter without haste. This opening is a boundary between two connected environments. A cave is a naturally occurring underground void that is large enough for a person to enter. Yet the passage we can see is only part of a greater underground system. Beyond its walls may be smaller cavities, narrow cracks, pockets, and channels that no person could pass through. These hidden spaces still matter. Water can move through them, minerals can gather within them, and small forms of life may find suitable places there. At the entrance, the surface and underground environments meet. Evening light reaches beneath the arch, becoming softer as it travels inward. Rain may blow into this sheltered space. Leaves gather near the threshold, carried by wind, animals, or flowing water. The air changes with the seasons and with the passing hours. Temperatures rise and fall more readily here than they do in the deeper cave. Sunlight, rain, leaves, animals, and changing temperatures all influence the entrance. Their influence becomes weaker farther underground. Deep within the cave, sunlight does not reach, temperatures change more slowly, and the weather above feels distant. Here at the mouth, however, the two environments overlap. Mosses and other plants grow where enough filtered light remains. Insects move among the damp leaves. Animals may visit the shade before returning to the open landscape. The cave entrance belongs partly to the hillside and partly to the sheltered world beneath it. We pause beneath the limestone arch. The air is cooler here than it was along the path. It carries the quiet scent of damp stone and earth. Behind us, the familiar landscape remains visible. There is grass, a line of trees, the silver ribbon of the stream, and a sky slowly deepening toward evening. Before us, the passage slopes gently into shade. This journey does not belong to one particular named cave. It represents a limestone solution cave. A cave formed as water slowly opened spaces within limestone. Real caves differ greatly from one another, and no single cave contains every feature we will encounter. Some caves hold streams, while others are dry. Some open into broad chambers, while others remain narrow. Certain caves contain delicate mineral formations, but others have few. Bats live in some caves, though not in all of them. Fossils, bones, or archaeological material may be preserved in certain places and entirely absent in others. The cave we enter is therefore a gentle gathering of features found across many limestone regions. It gives us a way to follow water, stone, crystals, darkness, and life along one calm and carefully guided route. Real caves may include flooding, unstable rock, poor footing, or difficult air conditions. On this journey, our route has been checked and controlled. We remain with our guide and follow firm, established paths. Around us, the cave may be understood as a natural archive, although it is not an orderly library. Over long spans of time, caves can preserve many forms of evidence. Thin mineral layers may hold clues about water and past climate. Sediments carried by streams may settle across the floor. Fossils and bones can remain within protected deposits. Pollen and fragments of plants may survive in sheltered layers. Archaeological objects can preserve signs of people who once entered or used a cave. Sand, clay, and marks left upon stone may also reveal the passage of old floods. A corridor that seems dry today may once have carried flowing water. Sediment left along a wall or ledge can show that floodwater once reached higher than the present stream. Layer by layer, the cave may hold traces of conditions that have long since changed. Yet preservation is never automatic. A cave is not sealed away from time. Floods can lift and rearrange sediment. Flowing water may erode an older layer. Animals can disturb bones or move plant material from one place to another. Visitors may shift something without realizing its importance. Later mineral growth may cover an object or alter the layers around it. For this reason, those who study caves look closely at the setting of every discovery. They ask what has been preserved, how it arrived, whether it has moved, and what may have happened since it first came to rest. The archive is patient, but it is always changing. Above the entrance, the limestone hillside appears still. Its history, however, reaches much farther into the past than the hollow within it. The rock surrounding a cave can be far older than the cave passage itself. Limestone may have begun as sediment in an ancient sea, hundreds of millions of years before groundwater opened pathways through it. Material settled and accumulated, and over immense spans of time, those sediments became solid rock. Much later, groundwater began to enlarge spaces within the limestone. The stone and the passage therefore have different ages. The rock may belong to a distant marine landscape, while the cave is a younger opening formed within it. We do not need to measure all of that time at once. Here at the entrance, it is enough to notice how many histories can share one quiet place. There's the ancient history of the limestone itself. There's the later movement of water through cracks and hidden channels. There are records of changing rainfall and climate. There are sediments carried by floods, traces left by animals, and signs of brief human visits. Each belongs to a different moment, and each may rest beside the others beneath the same sheltering hill. A drop falls somewhere beyond the shaded bend. Its sound is small and rounded. It touches the stone, and then fades into the spacious stillness. After a quiet pause, another drop follows. The rhythm is slow and unhurried. Outside, the stream continues beneath the evening light. Within the entrance, moisture gathers upon the limestone wall. Both are part of the broad movement of water across the land and through the ground below. For a moment, we remain at the threshold. Behind us, the leaves stir softly along the path. The sky is still visible between the trees. Ahead, the cave holds its steady shade. The entrance connects these places, rather than separating them. Surface water enters the ground. Underground air reaches toward the hillside. Animals, leaves, and sediment may pass from one environment into the other. Cooler air moves gently from the opening, carrying the quiet presence of the sheltered passages ahead. We take one last look at the pale evening sky, the grass, the leaves, and the nearby stream. Then our attention turns toward water beginning its slower journey, far above the cave. Rain settles upon woodland and grass. It reaches the soil and gathers among roots. Some of it follows the surface toward streams. Some enters small openings in the earth and moves gradually downward, through narrow spaces and into the limestone below. There, beyond the reach of evening light, water meets stone. In the next part of our journey, we will follow that quiet rainwater beneath the surface. We will see how it passes through soil, enters cracks, and begins the patient work that can open the first hidden spaces in limestone. For now, we stand comfortably beneath the broad arch, listening to the steady fall of distant droplets, while the cave and the evening landscape rest together. Chapter 2: How the Hollow Begins. Rain settles softly upon the land above the cave. Some droplets rest for a while on leaves. Others gather along blades of grass, slip from their narrow tips, and reach the ground. A little water collects in shallow hollows or joins a surface stream. Much of it, however, begins a quieter journey. It sinks into the soil, passing between grains of sand, fragments of fallen leaves, and the fine threads of living roots. During its fall through the air, Rainwater absorbs a small amount of carbon dioxide from the atmosphere. Then, as the water enters the soil, it usually gathers more. Plant roots release carbon dioxide through their ordinary life processes. Tiny organisms release it as they break down leaves and other natural material. Because of this activity, the small spaces within soil can contain more carbon dioxide than the open air above. Water and carbon dioxide combine to form weak carbonic acid. The word acid may sound severe, but this solution is mild. Its work is neither sudden nor forceful. Yet when weakly acidic water returns again and again, over long spans of time, its gentle chemistry can reshape an entire landscape. Below the soil lies limestone, a rock made mostly of a mineral called calcium carbonate. The weakly acidic water can dissolve this mineral. Limestone does not vanish quickly, as sugar seems to disappear when stirred into a warm drink. The change is much slower. Water reaches the stone, remains in contact with it, and carries away only small amounts of mineral. The work is often too gradual for any single observer to notice. Yet the water continues to descend after every rainfall, and the quiet process is repeated. The water does not usually make its way through perfectly solid stone. Instead, it follows weaknesses and openings that are already present. Limestone may contain joints, fractures, faults, and bedding planes. Bedding planes are the boundaries between separate layers of rock. There may also be tiny pores, narrow gaps, and irregular spaces that provide roots for water. The descending water enters these small openings. Along their walls it dissolves minute quantities of limestone. A hairline crack becomes a little wider. Once widened, it can admit more water. The greater flow continues the work, carrying dissolved material away and allowing still more water to pass. Little by little, a route that was once almost invisible may become a narrow channel. The channel may widen into a conduit, carrying water through the rock. In favorable conditions, that conduit can continue to enlarge until it becomes part of a cave passage. The hollow does not begin with one droplet acting alone. It is shaped by an immense succession of droplets, each taking part in the same peaceful cycle. Rain falls from the sky, it enters the soil, it gathers carbon dioxide, it reaches the stone, follows its smallest openings, and travels onward toward lower ground. A landscape shaped by the dissolving of soluble rock is known as karst. Limestone is commonly associated with karst, although other soluble rocks can also form karst landscapes. From above, such a place may seem quiet and familiar. There may be wooded hills, open meadows, shallow valleys, and streams moving through the grass. Yet beneath this ordinary surface lies an unseen pattern of water. A stream may cross the land and then disappear into an opening. Instead of continuing through an open valley, it may travel beneath a hill. Farther away, water may emerge again at a spring, clear and cool after following hidden roots through the stone. For a moment we can picture that landscape from above. Rain lies on the leaves, water gathers among the roots, a small stream passes between low banks and then quietly slips underground. Beyond the place where it disappears, the surface channel may be dry, while the water continues its journey below. Karst landscapes may contain caves, springs, disappearing streams, underground drainage, and sinkholes, each as part of the close connection between water at the surface and water beneath it. A sinkhole is a closed depression in the land, a place where the ground slopes inward rather than draining through an ordinary surface valley. Some sinkholes form gradually as soluble rock is lowered by dissolution. Others develop as loose soil settles into openings below. Not every sinkhole appears through a sudden collapse. Many are broad, gentle features that have taken shape slowly. Grass may cover their slopes. Trees may grow around their edges. Rainwater may collect in the lower ground before finding a hidden route downward. The connection between the surface and the cave may remain out of sight, but the moving water joins them. Beneath the hills, water continues to follow gravity. Some travels downward toward the water table. Below this level, the available openings in the rock are filled with water. Some cave passages begin near or below the water table, while they are completely flooded. Water moves through submerged fractures, bedding planes, pores, and other openings, dissolving the surrounding limestone. Because a developing passage is full of water, dissolution can take place along its ceiling, floor, and walls. Over time, a rounded or tube-like route may form. Later, the pattern of drainage can change. The surrounding landscape may also change in elevation. The water table may move downward, leaving an older passage above it. A route that was once completely filled with water can then become air-filled. The water continues through deeper levels, while the older passage remains behind. Small pools may rest in hollows, droplets may gather on the ceiling, cool air may occupy the space that water once filled. The shape of the passage quietly preserves something of its earlier history. This is the common beginning of many familiar limestone caves. They are known as solution caves because they form as water-dissolved soluble rock. Yet not every limestone cave has been shaped mainly by carbonic acid descending from the surface. Cave systems do not all share exactly the same history. In some major cave systems, sulfuric acid has played an important role in dissolving limestone. This is a different chemical path from the familiar journey of rain through air, soil, and stone. The details vary from place to place, but the result can still be an extensive network of solution passages. Whatever the pathway, the dissolved limestone does not simply cease to exist. As water moves through the rock, it can carry calcium and bicarbonate in solution. These materials are invisible within the clear water. They travel through pores and fractures, through narrow channels, and sometimes through broad underground streams. Later, some of that mineral matter may become visible again. When mineral-bearing water enters an air-filled cave, it may lose some of its carbon dioxide. As the chemistry changes, calcium carbonate can be deposited once more. A tiny amount may remain where a droplet rested on the ceiling. A pale film may form along a wall or floor. Repeated deposits can eventually build the stalactites, stalagmites, and flowing sheets of stone found farther within the cave. Those formations will have their own part in our journey. For now, it is enough to notice that water can perform two patient tasks. In one place, water dissolves limestone and opens a route. In another place, under different conditions, it leaves calcium carbonate behind and begins to create a new form. Dissolving and depositing belong to the same long circulation of water and mineral through the cave. Above us, rain continues to settle into the soil. Below, hidden water gathers, separates, and meets again. One slender thread follows a bedding plane, another descends through a fracture, a third moves slowly through pores in the rock. Several routes join, forming a larger channel that bends through the limestone. Farther on, the water may enter an underground stream. It may remain beneath the hills for a time, then rise into daylight at a spring in another valley. The spring, the disappearing stream, the sinkhole, and the cave are not isolated features. They are parts of one connected drainage system, shaped by water moving between the visible landscape and the sheltered world below. At first, many of the hidden channels are too small for anything but water. Their walls are close together, and no surface light can reach them. Yet the slow dissolving work continues. Some channels gradually widen into conduits, and some conduits become passages where air can enter. Near the edge of the hillside, one such passage opens toward the outer world. Daylight rests at its entrance and reaches a little way inward. Ferns and mosses remain close to the opening. Beyond them the light becomes softer, and the cool stillness of the cave grows deeper. Behind us lies the rain-washed landscape, with its soil, roots, streams, and hidden openings. Ahead lies the gentle boundary where the surface begins to fade. We follow that diminishing light into the quiet borderland between outside and below. Chapter 3. The Twilight Passage. The passage opens into the hillside, where the outer world rests within a frame of weathered stone. Behind us, grasses move gently beneath the open sky. Before us, the cave receives the daylight and slowly softens it. At first, the entrance feels closely connected to the landscape outside. Sunlight reaches the floor in pale, uneven shapes. A fern grows beside a shallow seam in the rock, its leaves turned toward the brightness. Moss covers a damp ledge with quiet green, and a thin layer of algae lends color to stone touched by both moisture and light. This first part of the cave is known as the entrance zone. It belongs partly to the surface and partly to the underground. The air here changes with the weather. On a warm afternoon, warmth may linger near the opening. After rain, the stones may darken with moisture, and small drops may gather beneath the lip of the cave. Wind can enter freely, carrying the faint scents of soil and leaves. Temperature and humidity, the amount of water vapor in the air, usually fluctuate most strongly near the entrance. Day and night can both be felt here, soak in the passing seasons. Winter air may settle into the opening, while summer warmth may reach across the first stones. Yet even here, the surrounding rock begins to moderate these changes. Stone warms and cools more slowly than open air, gently smoothing the sharper edges of each passing day. A small spider rests in a sheltered corner. Farther along, a frog sits beside a damp hollow, still and nearly the same color as the rock. Depending on the location and climate, cave entrances may shelter insects, spiders, frogs, salamanders, birds, or small mammals. They find refuge among ledges and cracks, while remaining close to the light and food of the surface. We continue without disturbing them. The floor slopes inward, and the green light begins to fade. It does not disappear at a single line. Cave zones are useful ways of describing underground environments, but their boundaries are gradual. One region blends quietly into the next, just as evening blends into night. A few steps farther in, direct sunlight no longer touches the walls. Instead, light arrives by reflection. It has traveled from the sky, the ground, and the pale stone near the opening. Here it appears silver rather than green, resting lightly on rounded surfaces. This is the twilight zone. The name describes a place where dim, indirect light remains, although it is no longer strong enough to support abundant plant growth. Photosynthesis is the process by which plants, algae, and certain other organisms use light to make food. As the light weakens, that process becomes increasingly limited. Moss may persist on a moist surface, facing the entrance. A delicate fern may grow from a crack, where a narrow thread of brightness still reaches. A faint, green film may remain on stone turned toward the outer world. Beyond that, leaves and green surfaces become sparse. There is no sudden end to life, only a gentle change in what life can use. The air feels cooler now, although a cave's climate is never determined by depth alone. Many sizable caves remain close to the surrounding region's mean annual surface temperature, which is the average temperature across all the seasons of a year. This is a helpful general rule, but not a promise. Elevation, moving water, cave geometry, multiple entrances, geothermal heat from within the earth, and the presence of ice can all alter underground conditions. A cave with several entrances may seem to breathe. When underground air and surface air differ in temperature, warmer air may rise, while cooler air sinks. Differences in atmospheric pressure can also move air gently through connected passages. The result may be a cool current passing across the hands and face, or a faint outward drift carrying the mineral scent of damp stone. Here, the movement is slight. It follows the curves of the walls and passes through openings too narrow to see clearly. The cave is sheltered, but it is not entirely sealed away from the surface. Air, water, warmth, and living creatures can all cross its gradual borders. Our footsteps soften over a patch of fine sediment. Each step makes a low sound, and then the passage settles again. In another chamber, the same sound might return as a distinct echo, but caves do not all answer in the same way. An echo depends on the size and shape of the space, the texture of its surfaces, and the location where the sound begins. Broad, smooth walls may send a sound back clearly. Rough stone may scatter it into many small reflections. A bending passage may allow the sound to fade quietly into the distance. Here there is only a rounded reply, brief and soft. The ceiling lowers slightly then rises once more. Along one wall, moisture has darkened the limestone. Cave humidity is often high and may approach saturation, the point at which air holds nearly as much water vapor as it can at that temperature. Yet not every cave is uniformly damp, and not every underground passage is wet. Some passages are dry. Others receive moving air that carries moisture away. Still others contain pools, streams, or walls covered with droplets. Even within a single cave, conditions may change from one chamber to the next. Deeper inside, the influence of surface weather becomes weaker. A warm afternoon outside may take time to affect the air within, if it affects it at all. Seasonal changes are usually reduced and delayed, filtered through layers of earth and stone. The farther we travel from the opening, the steadier the surroundings may become. The remaining daylight is now soft gray. Looking back, the entrance seems smaller, though it is still clearly visible. It holds the colors of the hillside within a distant oval. There are green leaves, pale sky, and the subdued gold of the ground. The view is calm and familiar, like a quiet picture set into the stone. Our eyes gradually adjust to the dimness. The pupils widen, allowing more light to enter, and the eyes become more sensitive over time. Shapes that first seemed uncertain begin to separate from one another. A ledge appears along the wall. A shallow hollow emerges in the floor. The passage continues as a gentle arrangement of gray forms. This adaptation can help human eyes in very faint light, but it has a clear limit. Farther within the cave lies the dark zone, where no natural visible light reaches. In absolute darkness, the eyes cannot form visual images. There is no light for vision to use. Nothing is wrong with the eyes. There is simply no visible light to receive. We have not yet reached that deeper region. For now, the last indirect brightness remains behind us, thinning softly across the stone. The entrance zone, the twilight zone, and the dark zone are not separate rooms with exact borders. They are descriptions of a long transition. Daylight diminishes from green to silver, and then from silver to gray. Photosynthetic growth becomes scarce. Daily and seasonal temperature changes become less pronounced. Surface sounds recede, allowing the quieter sounds of the underground to become easier to notice. We move a little farther, taking time to observe each subtle change. The damp stone reflects a final trace of brightness. The air remains cool against the skin. Behind us, the entrance still carries the distant weather of the hillside, while ahead, the passage holds a steadier calm. There is no abrupt crossing. The cave deepens by degrees. We pause near the far edge of the twilight zone. The walls carry only the faintest gray sheen. Behind us lies the broad world of weather, leaves, and sunlight. Ahead lies the more constant world beneath the hills. In this quiet, another sound gradually comes forward. It has been present for some time, hidden beneath our softened footsteps and the slight movement of air. Now it can be heard as a low, continuous murmur. Water is flowing over stone somewhere ahead. The sound follows the passage, smooth and unhurried. It rises gently into the stillness, inviting us onward toward a river beneath the hills. Chapter 4. A River Beneath the Hills. The murmur grows clearer as we continue beyond the twilight passage. It is not the sound of a great river filling a vast tunnel. Instead, it is the gentle voice of a shallow stream moving over smooth stone. Water slips around pale ledges, gathers in dark pools, and passes beneath shelves of limestone. Here and there, a ripple catches the faint light we carry, drawing a slender silver line across the surface. An underground river is not always broad or deep enough for a boat. It may be only a narrow ribbon, winding quietly along the floor of a passage. Elsewhere, the same flow may disappear beneath fallen stones, spread through gravel, or divide among cracks too small to enter. What we call an underground river can be one visible part of a much larger drainage system, hidden within the hill. We walk beside this calm stretch of water, where flat ledges offer an easy path. The air remains cool and even. Reflections shift slowly across the dark surface, and the stream's low murmur stays with us. Every drop in this stream begins somewhere above ground. Some may have fallen as rain onto fields or woodland. Some may have gathered in a surface creek that vanished into a sinkhole. Other drops entered the earth more quietly, soaking through soil, passing into fractured bedrock, and seeping downward across a broad area. Scientists who study water call this entry into an underground reservoir recharge. An aquifer is rock or sediment that can store and transmit water. In a limestone region, a karst aquifer may include tiny pores, narrow fractures, enlarged channels called conduits, and open cave streams. Water can travel through all of these spaces. Recharge does not happen through only one doorway. A sinking stream may carry water rapidly below ground. A sinkhole may collect rainfall from the land around it. Elsewhere, water filters gradually through soil and many small openings in the rock. The land supplying this underground system is its recharge area, and that area may extend far beyond the cave entrance. The stream bends around a smooth bank of sand. Small pebbles rest beneath the clear surface, their rounded shapes softened by moving water. The current is gentle now, but the arrangement of sediment shows that the stream does not always remain at this level. After prolonged rain, water can enter open conduits quickly. Unlike groundwater moving slowly through very small pores, Water in an open cave channel may travel with surprising speed. During wetter periods, lower passages can fill with water. During dry periods, the level may fall, exposing upper passages, gravel banks, smooth ledges, and sections of the cave floor that were previously covered. There is no need to imagine those changes unfolding now. In this quiet moment, the stream is shallow and steady, yet a smooth line of silt above the present water reminds us that the cave has seasons, just as the surface does. Here those seasons are measured not by leaves or blossoms, but by the rise and fall of hidden water. As the current moves, it carries more than water. Fine clay may remain suspended within it, while grains of sand and small pebbles roll along the bed. These particles brush and scrape against the cave floor. Over long spans of time, sediment abrades the stone, slowly wearing it through physical contact. This abrasion works alongside chemical dissolution, the gradual process by which slightly acidic water dissolves limestone. Dissolution enlarges cracks and openings. Flowing sand and gravel then rub against the surfaces, smoothing hollows and deepening channels. The rounded ledges beside us have been shaped by countless movements, most far too small to notice as they happened. The stream's quiet sound follows us onward. Although this water flows beneath the landscape, it does not always follow the boundaries visible above. On a surface map, hills and ridges divide watersheds, directing rain toward different valleys. Underground, however, fractures and conduits may pass beneath those divides. Water falling on one side of a ridge can travel through limestone and emerge on the other side, sometimes far from where it entered the ground. Because many of these routes are inaccessible, scientists use careful methods to trace them. They may place a small measured amount of a selected fluorescent dye where water sinks underground. Monitoring devices are positioned at springs, streams, or wells. If the dye later reaches one of those places, even at a concentration too faint to see without an instrument, it reveals a connection through the aquifer. Together with water level sensors and other monitoring equipment, dye tracing can help researchers estimate the direction and speed of underground flow. In this way, they can begin to map drainage routes through passages that no person can directly follow. Eventually, much of the water traveling beneath the hills returns to the surface. Water leaving an aquifer is called discharge. In karst country, discharge often occurs at a spring, where groundwater flows naturally from the rock into daylight. A spring may appear as a clear pool at the foot of a slope, or as a stream emerging beneath a wooded bank. Recharge is water entering the aquifer. Discharge is water leaving it. Between those two parts of the cycle lies a hidden journey through pores, fractures, conduits, and open cave streams. The water beside us may one day reappear in a spring far beyond this passage. It may join a surface river, flow through wetlands, or become part of a community's water supply. Karst aquifers can provide abundant groundwater, making them important to farms, towns, plants, and wildlife. Yet the openness of these systems also makes them vulnerable. Water can move rapidly through sinkholes and cave conduits, with limited natural filtration along the way. Pollution entering a sinking stream, a sinkhole, or fractured limestone may travel a considerable distance underground. Fuel, waste, fertilizer, and other contaminants can reach springs and wells sooner than people might expect. For this reason, underground water is not automatically pure or safe to drink, even when it looks perfectly clear. Protecting a karst aquifer means caring for the whole recharge area above it, including places that may seem far from any known cave or spring. What happens on the surface can become part of the river below. For a while we pause beside a dark pool where the current becomes almost still. A single ripple widens across the reflection, touches the limestone edge, and disappears. Then, the soft murmur returns, as the water narrows and continues along a natural weakness in the rock. Water has followed such weaknesses for immense spans of time. It has entered fractures and moved along the boundaries between layers of limestone. Some routes remained narrow. Others widened as dissolution and abrasion continued, becoming corridors large enough to carry an open stream. The peaceful water before us is only one quiet moment in a larger changing system. Rain is entering the earth somewhere above. Groundwater is moving through pores and fractures. Springs are returning it to daylight. Here beneath the hills, the stream continues between those two worlds. Ahead, the ceiling begins to rise. The water keeps to its polished course, while the space around it opens into ledges, arches, and shadowed recesses. The stream has followed weaknesses already present in the stone, gradually widening some places more than others. Beyond the watercourse, narrow routes give way to broader spaces. Guided by the structure of the limestone and enlarged by patient water, the underground path becomes a sequence of rooms and corridors, all quietly carved beneath the hills. Chapter 5. Rooms Carved by Water. The stream continues beside us, following its polished channel, as the ceiling rises beyond our lamplight. The walls draw farther apart, echoes linger, and the cave opens into a broad chamber whose upper curves remain in shadow. Our established path leaves the water's edge and crosses firm clay and settled sand. Pale marks on the wall show where the river has stood in wetter seasons, but the ground is calm and dry. Broad blocks of limestone rest nearby, their edges softened by time and thin mineral deposits. This underground room has been shaped by more than one process. Water began the work by dissolving limestone along natural weaknesses. Later, changes in the walls and ceiling altered the chamber further. Its form begins with the structure of the rock itself. Limestone often forms in layers. Many ancient limestones began as sediment on a shallow seafloor, where grains, shells, and the remains of marine organisms accumulated. Over immense spans of time, these materials were pressed and cemented into stone. The boundaries between layers are called bedding planes. Some are nearly horizontal, others have been tilted by movements of Earth's crust. The rock also contains cracks. Vertical cracks are often called joints, while larger breaks along which rock has moved are faults. Water need not create these openings. It enters weaknesses already present, then enlarges them little by little as weakly acidic groundwater dissolves the limestone. Where water follows a bedding plane, a passage may spread outward more easily than upward, becoming broad and low. Where it follows a vertical joint, the passage may grow narrow and tall. Where bedding planes, joints, and faults intersect, water can work in several directions at once, producing complex corridors and spacious rooms. The rock's structure quietly guides the route. Along one side of the chamber, our light reaches a smooth, rounded tunnel, whose walls curve gently into the ceiling. Such passages often developed while completely filled with water. The entire route lay below the water table, in the saturated part of the limestone, so flowing groundwater touched and dissolved the floor, walls, and ceiling, rather than running only along the bottom. Much later, the water table lowered, perhaps as a surface river cut its valley more deeply. The land slowly rose, or drainage patterns changed. Water then gathered into a stream along the passage floor and began cutting downward. A tall, narrow canyon could form beneath part of the older rounded tube, preserving two chapters in one route. First a groundwater-filled tunnel, then an open passage with a flowing stream. Elsewhere, descending rainwater and groundwater enlarge upright fractures into tall shafts, narrow slots, and rounded domes. A dome rises into the ceiling, like the inside of a stone bell. A shaft extends downward, though the name depends partly on viewpoint. Both can reflect water following a steep weakness. We stay on the level path, while the guide's light rests on one smooth, gently scalloped dome. Large rooms may develop where passages meet, where limestone is especially soluble, or where many fractures let water approach from several directions. Once an opening has grown, unsupported stone may respond to gravity. Pieces separate from the ceiling or walls and settle below. Cave scientists call this fallen material breakdown. The word may sound dramatic, but much breakdown is ancient and still. The broad blocks before us may have rested in place for thousands of years. Established visitor routes are carefully chosen and monitored, allowing quiet, safe observation. Falling blocks can widen a room, reveal a higher ceiling, and create ledges or slopes. Later, water may carry clay and sand between the stones, while thin mineral coatings soften their surfaces. Yet breakdown usually did not create the cave's first opening. Before a ceiling could fall into a room, water had already dissolved space within the limestone. Fallen rock modified that solutional chamber rather than beginning it. Water made the hollow, and gravity changed its shape. We pause beside a low railing and look across the chamber. Size alone cannot reveal exact age. A large room may occupy highly fractured rock, mark a junction of passages, or have been enlarged by breakdown. A narrow corridor elsewhere may preserve a route of equal or greater age. Cave history must be read from many clues together. Beyond the chamber, an other opening belongs to an earlier cave level. Many systems contain several levels, with older abandoned passages above streams that remain active. As land slowly rises, a surface river deepens its valley, or drainage changes, the regional water table may descend. Groundwater then finds lower routes through the limestone, leaving former passages dry while newer ones develop beneath them. Repeated over long periods, this process can produce stacked former water routes and active drainage corridors. An upper passage may preserve a vanished underground river while modern water continues through a younger channel far below. The levels are not perfectly flat or evenly spaced. Water follows bedding planes and fractures that slope, bend, and intersect, creating not regular floors, but a quiet network adjusted to the surrounding stone. Some upper passages are dry and have few mineral decorations. A layer of sandstone or shale above may limit water seeping from the surface, acting as a protective cover and directing moisture elsewhere. Without steady seepage, an abandoned corridor can remain plain, showing the clean lines and muted colors of its rock. Other upper passages receive abundant mineral-rich water. Their ceilings and walls may carry delicate formations, shining curtains, or broad calcite deposits. Two passages at similar heights can therefore look quite different. Their appearance depends not only on position or age, but also on the route taken by water above them. Clay and sand offer further signs of change. A quiet current may leave fine sediment across a floor, stronger flow may carry some farther along. Layers can remain undisturbed in sheltered corners, then be reshaped if the stream returns. The cave is not one room made at one moment, but a connected landscape altered in stages as water finds new paths. The chamber settles into spacious silence. Below us, the modern stream continues through its lower corridor. Above lie former water routes, preserved like outlines of vanished rivers. Around us, rounded tubes, descending canyons, vertical domes, clay banks, settled sand, and resting blocks belong to one long history. Each shape records changing conditions, after the water that formed it has moved on. Water entered small weaknesses, enlarging bedding planes, joints, and faults. In some places it filled entire tunnels, in others it flowed as an open stream and cut downward. As water tables changed, active flow shifted lower and left earlier levels behind. Gravity reshaped chambers, and sediment gathered across their floors. Through it all, the underground landscape changed without haste. Each room and corridor reflects a particular meeting of stone, water, and time. Some spaces are broad, others are narrow or tall. Some remain active routes, while others have been dry and still for ages. No chamber can be understood. Chapter 6. The Patient Work of a Droplet. In a sheltered passage above the underground river, a droplet gathers on the cave ceiling. It has traveled slowly through soil and limestone, following pores too small to see and narrow fractures hidden within the rock. Along the way, the water dissolved a little calcium carbonate from the limestone around it. Now it has entered the open air of the cave, carrying that mineral in a clear, almost invisible solution. The droplet swells. For a moment, it hangs quietly beneath the stone. When mineral-bearing water enters an air-filled cave passage, some of its carbon dioxide may escape into the cave air. As the water loses carbon dioxide, it can no longer hold quite as much dissolved calcium carbonate. A very thin mineral layer may then be left behind, often as calcite, a crystalline form of calcium carbonate. Then the droplet falls. Its mineral trace is so slight that we might not notice it. Yet another droplet gathers in the same place, following the same tiny route through the ceiling. It too releases carbon dioxide. It too leaves a nearly invisible ring of calcite before falling away. Repeated over long and irregular spans of time, these fine deposits can create a speleothem. A speleothem is a mineral deposit formed in a cave. The word describes the deposit's form and underground setting. It does not name one particular mineral. Many familiar speleothems in limestone caves are made mainly of calcite, though cave deposits can contain other minerals as well. The first visible shape may be a narrow tube descending from the ceiling. This is called a soda straw. It is hollow, slender, and often remarkably delicate. Water moves through its center and gathers at the open tip. There, the droplet waits, leaves a ring of mineral, and falls. Each new ring extends the tube by a minute amount. Some soda straws remain thin, others begin to change. Water may start flowing over their outer surfaces, depositing calcite around the outside and gradually making the formation wider. In this way, many common calcite stalactites begin as soda straws. A stalactite grows downward from the ceiling. Some are tapered and graceful. Others become thick and rounded, their surface is marked by faint ridges left by changing paths of water. Their shapes depend on more than time alone. Water chemistry, drip rate, temperature, airflow, evaporation, surface vegetation, and other local conditions can all influence how calcite is deposited. Even nearby stalactites may grow differently. One may receive a steady thread of water, while another is wetted only after rain. A third may become dry because the root above it has changed, or because the water has found an easier path elsewhere. Speleothem growth is often intermittent. A formation may grow for a time, pause for years or far longer, and begin again if water returns. There is no universal growth rate. Mineral layers gather comparatively rapidly. Under others, growth is extremely slow. Sometimes there is no growth at all. The cave keeps no simple schedule. The droplet that leaves the stalactite now falls toward the floor. When it lands, it spreads outward and releases more carbon dioxide. Another thin layer of calcite remains at the place of impact. Drop follows drop, each one adding a trace to what came before. Slowly, the deposit builds upward into a stalagmite. Stalagmites are often broader and more rounded than the stalactites above them. Some resemble low mounds, others rise as smooth cones or sturdy towers. Their forms reflect the way water lands, spreads, and deposits its mineral burden across the growing surface. Above, the stalactite reaches downward. Below, the stalagmite builds upward. If their growth continues along the same line, the two may eventually meet. Once joined, they form a column, also called a pillar, connecting ceiling and floor in one continuous mineral structure. Elsewhere in the chamber, water does not gather into separate drops. Instead, it travels as a thin film across a wall or down a gentle slope. As it flows, it releases carbon dioxide and leaves calcite in broad layers. The resulting sheets and mounds are known as flowstone. Flowstone follows the contours of the rock beneath it. Layer settles over layer, smoothing rough surfaces into rounded folds. The water continues quietly across the stone, leaving a fine mineral covering as it passes. Over time, a bare wall or floor may become draped in solid flowing shapes. Along a sloping ceiling, a droplet may follow the same curving edge before it falls. Mineral gathers along that route, gradually producing a thin, folded sheet called a drapery. Draperies hang in gentle curves. Their folds preserve the repeated path of water over the sloping stone, each layer resting upon an earlier one. Once again, we can imagine the droplet. It gathers, moves along the ceiling, and leaves a trace. Another follows, then another. The work is quiet, repeated, and patient. Near the cave floor, shallow pools create still other forms. At the edge of flowing water, mineral may gather into low barriers called rimstone. These small mineral dams can form around pools or across gentle flows. Water passes over their rims in a fine sheet, depositing more material along each boundary. Within some shallow pools lie cave pearls. A cave pearl begins around a small grain, fragment, or other tiny center. Mineral coatings gather around it in successive layers. Movement in the pool may shift or turn the growing pearl and help prevent it from attaching to the pool floor. Over time, the layered object can become rounded and smooth, resting within its shallow mineral basin. Not every cave pearl is perfectly spherical, and not every pool produces one. As with all speleothems, its form depends on local conditions, including the chemistry of the water, the available mineral, and the pattern of movement within the pool. Higher on a wall, we may notice formations that twist sideways, branch into delicate arms, or curl back toward the rock. These are helictites. Their shapes can seem surprising because they do not simply point downward, yet they do not defy gravity, and no mysterious process is needed to explain them. Helictites are influenced by several ordinary physical forces working on a very small scale. Capillary forces can draw water through narrow spaces. Tiny internal channels guide moisture through the growing formation. The direction of crystal growth also matters, as does airflow across the surface. Together, these influences can produce branching, curling, and twisted forms. Each shape around us is a record of movement. Water travels through stone, it passes through the hollow center of a soda straw, it gathers at the end of a stalactite, falls to a stalagmite, spreads across a wall as flowstone, or follows the edge of a drapery. It moves over a rimstone dam, circles through a shallow pool, or creeps through a channel finer than a thread. And at every stage, local conditions matter. A change in drip rate may alter the shape that grows. A shift in temperature, airflow, evaporation, water chemistry, or vegetation above the cave may change how much mineral is deposited. A water route may close, leaving a formation dry and still. Much later, moisture may return, and growth may quietly resume. This is why the size of a formation does not reveal a simple steady clock. One cannot assume that every layer took the same amount of time. Cave formations may grow rapidly, extremely slowly, intermittently, or not at all. Their histories are shaped by changing water routes and changing conditions, with pauses woven between periods of growth. The formations appear solid and enduring, yet their surfaces are easily altered. A touch can break a narrow soda straw or a delicate helictite. Contact can stain or soil calcite. It can also change the way water spreads across a surface and interfere with later crystal growth. For this reason, we remain on the established path. We observe without touching, allowing every drop and mineral surface to continue undisturbed. Once more, a droplet gathers above us. It rounds beneath the ceiling and waits. A little carbon dioxide passes from the water into the cave air. A layer of calcium carbonate, too fine for the eye to measure, remains behind. Then the droplet falls, and the chamber returns to its quiet rhythm. Above, a stalactite continues downward. Below, a stalagmite receives the falling water. Across a wall, flowstone gathers in broad sheets. Along a slope, a drapery preserves the curving path of moisture. Near the floor, rimstone borders a still pool, and a cave pearl rests within its shallow basin. On another surface, a helictite follows its tiny internal channels into a branching form. All are speleothems, all are cave deposits shaped by mineral-bearing water and the conditions around it. Yet no two have precisely the same history. Each records its own sequence of gathering, flowing, falling, pausing, and beginning again. The familiar forms of dripstone are only part of the underground mineral world. Beyond this chamber, in quieter corners and drier passages, crystals can gather in many other delicate forms. Chapter 7. Crystal Gardens. In the quieter corners of the cave, beyond the steady rhythm of falling droplets, the mineral world takes on finer and more varied forms. Along the protected path, the guide's shaded light moves slowly across walls, ledges, and shallow hollows. Small points answer with a muted glimmer. Some are cream or white, some are translucent gray, others carry soft shades of amber and rust. These are the crystal gardens of the cave. They have no leaves, roots, or petals, yet their branching and radiating shapes sometimes resemble plants. They grow according to the quiet rules of chemistry. Water moves through stone, minerals dissolve. Under suitable conditions, new solids form. A mineral is a naturally occurring solid with a characteristic chemical composition and an ordered internal structure. Its atoms are arranged in a regular pattern, even when that pattern is far too small to see. A crystal is a mineral whose internal order is expressed in its outward shape. That shape may appear through smooth faces, sharp points, slender blades, or repeated angles. Not every mineral deposit in a cave displays obvious crystal faces. Many cave deposits are made of grains so fine that they appear smooth, cloudy, or wax-like. Their internal structure is still ordered, but the individual crystals are too small to distinguish. Other deposits have formed where there was enough open space and where conditions allowed visible points, fibers, or blades to develop. In many limestone caves, the most common mineral in cave formations is calcite. Calcite is calcium carbonate, the same chemical compound that makes up much of the surrounding limestone. As mineral-bearing water moves through the cave, calcium carbonate may be deposited, gathering in layers or growing into recognizable crystal shapes. Pure calcite may look clear, translucent, or white. Here one patch resembles pale glass beneath a veil of moisture. Nearby another surface has the soft color of cream. Farther along the wall, pointed crystals line a shallow cavity. These pointed calcite crystals are known as dogtooth spar. The name is simply descriptive. Their narrow tips were thought to resemble the teeth of a dog. Dogtooth spar may line cavities or coat open surfaces, creating quiet fields of crystal points. Some crystals are tiny, no larger than grains. Others have more room to grow, allowing their faces and angles to become easier to see. We observe them without touching. Even where a formation appears sturdy, contact can damage a surface that has remained undisturbed for a very long time. The path gives us a clear view, while the crystals remain part of the cave that formed them. A little farther on, the shapes become thinner. Slender needles extend from a sheltered wall, and delicate branches spread like pale frost. These may be crystals of aragonite. Aragonite has the same chemical composition as calcite. Both are calcium carbonate, yet their atoms are arranged in different internal structures. That difference changes the ways in which the two minerals may grow. Calcite and aragonite offer a gentle reminder that chemical composition is only part of a mineral's identity. The arrangement of its atoms matters as well. Two minerals can contain the same chemical elements in the same proportions, yet take on different structures and different outward forms. Under suitable cave conditions, aragonite may grow as straight needles, branching clusters, or delicate frostwork. The smallest branches can seem almost weightless. They extend into the still cave air without soil or sunlight. Their forms arise from mineral structure and from the particular conditions around them. We pause while the guide's light rests beside the cluster rather than directly upon it. In the softer illumination, the aragonite appears white at its tips and translucent gray near the wall. Its beauty comes from natural structure alone. No mystical or supernatural quality is needed. The ordered pattern of the mineral, expressed patiently through time, is remarkable enough. The protected path continues into a somewhat drier part of the cave. Here another mineral may appear. It is gypsum. Gypsum is hydrated calcium sulfate. The word hydrated means that water is included within the mineral's chemical structure. Gypsum is therefore chemically different from calcite and aragonite, even though all three may form pale and delicate cave deposits. Gypsum can appear as a crust, a cross stone. It may also grow as needles, long fibrous crystals, or curling forms called gypsum flowers. The word flower describes the formation's appearance, not its nature. Gypsum flowers are not plants. They do not have roots, produce seeds, or turn toward the light. Their resemblance to petals is only a resemblance of shape. A gypsum flower begins as crystals grow outward from a wall or another surface. As the crystals continue to extend, the formation can curve. Fine blades and fibers may gather into pale clusters resembling folded petals or soft ribbons. Some remain close to the rock. Others bend gradually into the open passage. Gypsum displays often occur in relatively dry cave conditions. There, the pale mineral may form crusts, fibers, needles, or flowers. Each shape reflects the local conditions in which the crystals developed. One gypsum crust beside the path has the soft white appearance of chalk. Another is faintly translucent. Its long fibers catch the shaded light, but the glow remains subdued, like a thin cloud seen in evening air. The different forms are memorable. Calcite may gather into pointed dog-tooth spar. Aragonite may extend as needles, branches, and frostwork. Gypsum may spread into crusts or curve into fibrous flowers. Each mineral follows the possibilities of its own internal structure. It is easy to assume that every glittering surface underground is quartz, because quartz is a familiar crystal in the surface world. Yet not all glittering cave material is quartz. In many limestone caves, calcite is far more common. Aragonite and gypsum can also produce shining points, blades, and fibers. A passing glance is not enough for a reliable identification. Even color, vivid though it may seem, cannot identify a mineral by itself. Pure calcite may appear clear, translucent, or white, but natural cave formations frequently contain traces of other substances. Iron-bearing material often contributes yellow, orange, red, rust, or brown tones. Manganese compounds in organic material can produce darker coloration. Lighting also changes what the eye perceives. A cream-colored surface may appear warmer beneath one light and cooler beneath another. Moisture can deepen a color or give the surface a temporary shine. Small impurities may alter the appearance of a deposit. Thin microbial films can also tint, soften, or darken a mineral surface. For this reason, the colors in the crystal garden are clues rather than certain answers. Amber does not name a mineral. White does not guarantee purity. A translucent gray point may look different when it is wet, when the angle of light changes, or when a fine film lies across its surface. The cave asks for careful observation and patient study. Microbes also have a place in this mineral world. These extremely small forms of life may help produce or modify some unusual speleothems. Their influence differs from cave to cave, and from one formation to another. Some mineral deposits are affected by microbial activity, while others form mainly through non-living processes. The crystal garden is therefore not a single, simple display. It is a meeting place of rock, water, air, dissolved minerals, and in some locations microscopic life. Each formation reflects a particular set of conditions. Variations in moisture, chemistry, and the root of a thin seep may be expressed in a different texture or shape. A smooth coating may contain crystals too fine to see. An open cavity may hold pointed calcite. A sheltered wall may support aragonite needles. A relatively dry passage may preserve a curling gypsum flower. All are mineral records of the places in which they formed. Chapter 8. The Deepest Darkness. The guide's shaded lamp remains before us, casting a low circle across the path. Within that gentle light, the limestone floor appears in quiet shades of gray. Small ridges rise beneath our steps. A thin ribbon of sediment follows one edge of the passage, left behind by water that once moved here more freely. Beyond the lamp's reach, there is no color to see. We have entered the cave's dark zone. This is the part of the cave that receives no natural visible light from an entrance. Daylight cannot follow all the turns behind us. It cannot pass through the solid hill above. Here the familiar cycle of sunrise and sunset leaves no visible mark. The guide keeps the lamp steady, and the path remains clear. Its glow reveals only what is nearby. We see a sloping wall, a pale vein of calcite, and several droplets gathered along a ledge. Farther away, beyond the edge of illumination, the chamber continues unseen. A single drop falls. It meets a shallow pool with a quiet, rounded sound. Then there is time before the next one. At the surface, human eyes can adjust as evening gathers. The pupils widen, and the eyes become more sensitive to faint light. Stars emerge. Paths that seemed hidden begin to take shape. Complete cave darkness is different. When no visible light is present, the eyes have nothing to collect. No matter how long they adapt, they cannot form a useful image without light. This is not a failure of vision. It is simply how sight works. A visible image requires light reflected from a surface and received by the eye. Where there is no light, there can be no visible picture. For a moment the guide lowers the lamp and covers most of its glow with one hand. A narrow line of light still rests at our feet, enough to keep the path and the group gently connected. Around that small line, visual detail fades. There is no need to search the darkness for shapes. Nothing around us has changed, except the amount of light available to our eyes. The walls remain where they were. The floor continues beneath us. The guide is close, and the shaded lamp is ready. Freed from the need to examine distant forms, attention settles elsewhere. The texture of the floor can be felt through each careful step. Some places are firm and smooth. Others carry fine grains of sand or shallow ripples preserved in sediment. The air rests cool against the face. Moisture softens it. A faint current passes from one passage toward another, gentle enough to be sensed against the skin. Human hearing does not suddenly become more powerful in the dark. The ears do not transform when the lamp is lowered. Instead, we may pay closer attention to sound, because vision is providing less information. Small details that might have gone unnoticed now come forward. There's the drip again. Beyond it lies a softer sound, continuous and low. Perhaps along a channel hidden by stone. From behind us comes the muted rhythm of another person's footsteps. Fabric brushes lightly against fabric. Farther ahead, air moves through a narrower opening with a quiet murmur. Darkness does not create silence. Every cave has its own soundscape, shaped by water, moving air, animals, people, and the forms of the passages themselves. A falling droplet may sound sharp in one place and soft in another. Wind may whisper through a constricted corridor. A subterranean stream may fill a chamber with a steady tone. The movement of an animal may briefly stir sediment near a wall. Distant human steps may travel around a bend and reach us as a faint, measured rhythm. The cave changes these sounds as they travel. In a large chamber with broad, hard walls, a voice or footstep may return as an echo. Sound spreads outward, meets the stone, and reflects toward the listener. If the chamber is spacious enough, the returning sound may arrive after a clear pause. The guide speaks a few quiet words. The final syllable travels outward and returns, softened and slightly delayed. Then the chamber settles again into the sound of water. In another passage, there may be little echo at all. Irregular walls can scatter sound in many directions. Banks of clay, sand, or loose sediment can absorb part of it. A winding corridor may prevent sound from traveling far. One chamber can feel open and resonant, while the next seems gently hushed, even though both belong to the same underground system. The lamp brightens once more. Its warm circle opens across a wall marked by old water lines. The darkness remains beyond that circle, neither advancing nor retreating. Darkness is not a physical substance. It is simply the absence of visible light. That absence can feel restful because it asks so little of the eyes. There are no distant horizons to examine. There are no changing clouds, bright reflections, or moving patterns of sunlight and shadow. Within the guide's small circle of light, attention can remain close and unhurried. Yet the underground world has not become motionless. Deep cave conditions are often more stable than conditions at the surface. Outside, temperatures may rise during the day and fall at night. Seasons bring rain, dry weather, warmth, and cold. Far below, layers of rock soften many of these changes. Temperature and humidity may remain within a narrower range. Stable, however, does not mean static. Water continues to seep through cracks. Underground streams may rise and fall as rainfall and seasonal flow change. Air circulates where entrances, shafts, and connecting passages allow it to move. Minerals grow slowly along wet stone. Microbes metabolize, using energy and transforming substances around them. Animals travel between pools, crevices, chambers, and routes that connect the cave with the surface. Another cool current touches our hands as we pass an opening in the wall. It may connect with another passage, allowing air to move through the cave. Even at this depth, the chamber is part of a larger system. A drop falls behind us. Ahead, a thread of water continues over stone. The dark zone cannot support photosynthesis. Photosynthesis is the process by which plants, algae, and some microbes use light to produce energy-rich food. Without sunlight, green plants cannot grow here in the ordinary way. Most of the food energy in deep caves must therefore arrive from elsewhere. A stream may carry leaves, pieces of wood, or tiny particles underground. Roots may reach through cracks from plants growing above. Animals may enter and leave, bringing nutrients with them. Material may wash through sinkholes or descend with water and sediment. The surface and the cave remain connected, even where daylight cannot travel. In a few unusual cave systems, microbes gain energy from chemical reactions involving minerals or dissolved substances. They do not depend directly on sunlight in the same way that plants do. But they show that life can follow more than one path toward the energy it needs. The guide raises the shaded lamp toward the passage ahead. A smooth ceiling appears. Beneath it is a low shelf beside a narrow current of water. The light touches nearby stone, while the rest of the passage remains beyond its edge. We continue at an easy pace. The cave is dark, but it is not necessarily silent. It is sheltered, but it is not cut off from change. Water moves, air circulates, minerals gather slowly. Living cells continue their quiet work. For now, the darkness offers relief from visual demand. We need only follow the gentle light, notice the floor beneath us, and listen to the patient interval between drops. Sunlight does not reach this depth, but the cave is not empty. Along water, stone, sediment, and the roots that connect the cave to the surface, life has found quiet ways to continue. Chapter 9. Life Without Sunlight. The narrow thread of water continues beside us, clear where it crosses pale stone, and dark where it gathers in shallow pools. Within the gentle reach of the lamp, the passage seems still at first. Yet when we pause and look carefully, the cave reveals quiet signs of life. A faint film rests upon a damp wall. Tiny creatures move among grains of sediment. Farther along, a slender insect waits beside the water, guided not by daylight, but by touch, scent, vibration, and the subtle movement of air. Here in the dark zone, no natural visible light reaches the stone, photosynthesis cannot occur. There are no meadows of grass, no leafy shrubs, and no forest canopy. Even so, the cave is not separated from the living surface above. Energy enters by other, quieter routes. A leaf falling beside a stream may begin such a journey. Rain lifts it into the current and carries it through a crack, a sinkhole, or the opening of a disappearing stream. Underground, the leaf settles against a stone. Fungi and microbes begin to break it down. Small animals may feed upon the softened material, or upon the microbes growing across it. Other animals may then feed upon those small creatures. In this way, one leaf from the sunlit surface can become part of a food web in complete darkness. Wood, soil, and flood debris can travel along similar paths. Water may also bring dissolved organic matter. These are remnants of living things carried so completely within the current that we cannot see them. Visiting animals bring nutrients into the cave on their bodies, or leave nutrients behind in their droppings. Each contribution may seem modest, yet in a place where food is often limited, even a small fragment can support a patient community. The flow of energy is not always steady. One chamber may receive regular supplies from a stream, while another chamber, only a short distance away, receives very little. A seasonal flood may spread leaves, wood, soil, and sediment across a passage, then slowly recede. A piece of wood may remain for a long time, as fungi, microbes, and small animals gradually make use of it. Cave life is shaped by these long intervals. Food may arrive, remain for a while, and slowly diminish. Many underground organisms live at an unhurried pace, using what the cave provides with remarkable care. In some unusual cave systems, energy begins by a different path. Certain microbes use chemical reactions involving minerals or substances dissolved in water. They do not depend directly upon sunlight in the way that plants do. Instead, they obtain usable energy through cave chemistry. Such communities are not present in every cave. Still, they remind us that life can follow more than one route toward the energy it needs. A thin microbial coating on stone may be part of an intricate living system, even when it appears to be no more than a pale stain. The guide lowers the shaded lamp and invites us to listen. Above us, a few bats rest in the shelter of the ceiling. They are quiet nighttime animals, folded into still shapes against the rock. Depending on the species and the conditions within a cave, bats may come underground to rest, to find seasonal shelter, or to raise their young. Different species require different spaces, temperatures, and degrees of quiet. Not every cave contains bats. Even a cave used by bats may be occupied only during particular seasons. Many bats leave the cave to feed outside. Later, when they return to shelter, they bring some of that surface energy underground. Their droppings, commonly called guano, can provide food for fungi, microbes, insects, and other small organisms. In this way, a bat moving between the surface and the cave becomes a living bridge between two environments. It carries energy gathered beyond the cave entrance into passages untouched by daylight. Ecologists use the word troglodyte for an animal that regularly uses a cave, but must return to the surface for essential needs such as food. The word may be unfamiliar, so we can let its meaning settle slowly. A troglodyte is a regular cave visitor. It belongs to both journeys, inward and outward. Bats can be examples of troglodytes. They may rest safely underground, then travel outside to feed before returning to the cave. Other animals are more flexible. They can live within caves, but they can also survive in suitable environments outside. These animals are called troglophiles. Some salamanders, insects, spiders, and crustaceans may follow this pattern, depending upon the region and the species. They may favor the steady moisture and temperature of a cave, while retaining the ability to live in sheltered places nearer the surface. A troglophile, then, is comfortable underground, but not limited to the underground world. A third group has become more closely adapted to cave life. These animals are called troglobites. Troglobites are species that complete their entire life cycles underground. Over many generations, they have developed traits suited to environments without natural light. Some troglobitic animals have reduced eyes, because vision offers little advantage in permanent darkness. Some have reduced pigmentation, or less of the coloring seen in many surface animals. Others have elongated limbs, antennae, or other sensory structures. These can help them explore their surroundings through touch, or detect faint movements, currents, and vibrations. The adaptations vary from one species to another. A cave fish may have very small eyes or eyes that no longer function, A cave crustacean may rely upon long, delicate sensory structures. Some underground animals have slow metabolisms, meaning that their bodies use energy at a low rate. This may be helpful where food is scarce and long waits between meals are ordinary. There is no single design for cave life. Each species reflects its own ancestry, as well as the particular conditions of the cave it inhabits. As we continue beside the stream, we can quietly consider the many forms of life that may occur in caves around the world. Fish may inhabit submerged passages, salamanders may rest beside cool water, insects may move through damp sediment, while spiders wait near sheltered crevices. Pale crustaceans may live beneath the surfaces of pools, fungi spread through fallen organic material, microbes occupy water, mud, and stone, some are nourished by matter carried in from outside. In unusual places, others gain energy through chemical reactions. Each belongs to a web of exchanges that may be almost invisible to us. Yet no cave contains every kind of cave animal. Many caves contain no cave fish. Some are not suited to salamanders, or have no highly adapted dark zone species. The life found in any cave depends upon its region and its particular conditions. Water, food, and connections to the surface all help shape the community. A stream may carry nutrients into one passage, while leaving another nearly untouched. An animal visitor may bring energy into a chamber. A fragment of wood may support a small gathering of organisms for a long while. On wet stone, microbes may continue their work one cell at a time. Because food can be limited, cave organisms are often sensitive to disturbance. Some populations may grow slowly. Some species depend upon a narrow range of conditions. A small change in moisture, temperature, light, or activity may affect a habitat that has long remained stable. Noise and bright light can trouble resting wildlife. Footsteps may damage delicate habitat in sediment or shallow pools. Even when an animal appears motionless, it may be conserving energy that is difficult to replace. So we observe quietly and from a respectful distance. We do not touch the animals, disturb their shelter, or enter their resting places. We remain upon the established route, allowing the cave's living communities the space they need. The life here asks for no grand gesture from us. It asks only for care, patience, and room to continue. The stream moves onward, carrying minute particles through the darkness. Behind us, a leaf rests against a stone. Above us, a bat remains sheltered beneath the ceiling. Upon the wet wall, microbes continue their quiet work. Each is part of a connection extending from rain and soil to water, animal, mineral, and cave. Sunlight does not enter this deep passage, yet energy still arrives. It may be carried by a stream, held within a fallen leaf, brought by a visiting animal, or released through an unusual chemical reaction. In darkness, life continues without hurry. It waits, adapts, and makes careful use of what reaches it. And life leaves traces, just as water does. In settled mud, in mineral layers, and in the sheltered corners of caves, time can leave behind records for patient readers of stone. Chapter 10. Messages Written in Stone. The stream moves quietly beside us, carrying fine grains through the darkness. Some will travel onward toward a distant spring. Others will settle where the current slows, joining thin beds of sand and mud upon the cave floor. A fragment of leaf may come to rest among them. A grain of pollen may settle nearby. In time, mineral-rich water may cover them with a pale layer of calcite. In this way, caves become places where traces gather. They are sometimes described as natural archives. An archive is a collection of records preserved so that the past may be studied. Yet a cave does not arrange its records upon labeled shelves. Its pages may be folded, scattered, buried, or partly erased. To understand them, scientists must read patiently, examining each clue in its surroundings and comparing many different kinds of evidence. One record appears within speleothems, the mineral formations created by dripping or flowing water. Stalactites, stalagmites, and broad sheets of flowstone can contain layers formed at different times. A stalagmite rising from the floor may grow outward and upward in a series of very thin bands. In a carefully prepared scientific sample, these bands can resemble quiet rings or ribbons, each deposited as mineral-rich water reached the formation. The chemistry of that water is connected to conditions above the cave. Rain passes through the atmosphere, enters the soil, moves along cracks in the rock, and eventually reaches the chamber. During this journey, It carries chemical clues from the world above. Changes in rainfall, vegetation, soil activity, temperature, and the route taken through the stone may all influence the deposit that forms. By studying mineral layers and their chemistry, researchers can sometimes reconstruct parts of past climates. Certain forms of oxygen and carbon, together with tiny amounts of other elements, may reveal changes in the water that once fed a formation. In some caves, these patterns help scientists investigate wetter and drier periods. Elsewhere, they may offer clues about broader changes in climate and the surrounding environment. These clues must always be interpreted with care. A single layer does not necessarily have one simple meaning. Water may reach one chamber quickly, while water entering another chamber may travel slowly through the rock. Conditions can differ even between two formations standing close together. Scientists therefore compare samples, examine the cave's present water system, and look for agreement with records preserved elsewhere. Mineral growth is not always continuous. A stalagmite may grow for centuries, pause when its water supply shifts, and begin growing again much later. A dry surface, a change in crystal texture, or a thin coating of sediment may mark such an interruption. The formation remains a record, but some of its pages are missing. Beneath our feet lies another kind of archive. Cave sediments may include clay, silt, sand, gravel, and stones carried by water or released from the surrounding walls and ceilings. Their size and arrangement can reveal how water once moved through a passage. Fine mud generally settles where the water is gentle. Coarser sand or rounded pebbles may indicate a stronger current. A distinct layer of debris resting high upon a bank can preserve evidence of an earlier flood. These layers allow researchers to consider how underground streams change through time. Yet flowing water can also disturb what came before. It may cut into older deposits, carry grains away, and place them somewhere new. A bone, a stone tool, or a piece of charcoal may be moved far from the place where it originally rested. For this reason, location and surrounding layers can matter as much as the object itself. Caves can preserve fossils and bones from animals that entered the darkness, lived near an entrance, or were transported into the cave by water or other animals. Teeth and bones may reveal which species once inhabited the wider landscape. Even very small remains, including those of rodents, birds, reptiles, and amphibians, can provide valuable evidence about earlier environments. Pollen offers an even finer trace. Each grain is tiny, yet its shape can sometimes identify the group of plants from which it came. Pollen may enter a cave on air currents, in flowing water, upon animal fur, or within plant material carried by people. Seeds, charcoal, wood, and fragments of leaves may also survive within sheltered deposits. Together, these remains can offer clues about vegetation and surface environments. They may suggest whether the land outside once supported grassland, woodland, or another plant community. Near cave entrances, the archive may also contain evidence of people. Archaeological objects and other traces can reveal how caves were used in the past. Yet such materials must be studied in context. Their meaning depends not only upon what they are, but also upon where they were found and how they relate to the sediments, mineral layers, and nearby objects. An object resting beneath an undisturbed layer may tell a different story from the same kind of object found loose upon the floor. Careful mapping records position, depth, orientation, neighboring materials, and the order of deposits before anything is removed. Sampling is usually done with equal care so that the cave retains as much of its record as possible. Scientists can date some mineral layers by studying the gradual changes of naturally occurring elements. Some once-living materials may be examined through other dating methods. Researchers then compare the results with cave maps, sediment layers, fossils, pollen, plant fragments, chemical evidence, and signs of earlier floods. No single clue must carry the entire story. Greater understanding comes when several forms of evidence support one another. Even then, conclusions may be refined as new information appears. A cave is not automatically a perfect time capsule. Later mineral growth may seal an old surface beneath calcite. Burrowing animals may mix deposits. Floods may move bones, sediment, and archaeological objects. Erosion may remove entire layers. Visitors from much later periods may leave newer objects among older materials. The age of the surrounding rock does not provide a simple answer either. The rock may have formed long before the hollow passage developed within it. A stalagmite may be younger than the passage, and a bone resting beside it may be younger still. Rock, passage, mineral formation, sediment, fossil, and object can each belong to a different time. Cave passages and formations may develop over thousands to millions of years, but there is no single underground clock. Rates vary greatly. One formation may grow steadily for a time, while another remains unchanged through a long interval. Water routes shift, environmental conditions change, mineral growth pauses and begins again. Entrances may open or close, and chambers may fill with sediment before renewed water carries some of it away. The underground archive is therefore more like a long manuscript, written by many quiet hands. Water has written upon it. Mineral, animal, plant, climate, and people have added their traces. Some lines remain clear, others overlap, some have faded, while still others rest beneath later layers unseen. Beside us, the stream leaves a narrow border of fresh silt along its bank. Above it, an older band of clay lies beneath a pale mineral crust. Each layer belongs to a different moment, although its exact story is not immediately visible. Careful readers do not ask the stone for more certainty than it can provide. They map each place. They record relationships. They take careful samples and establish dates where possible. They test their ideas and compare the cave's evidence with records from beyond it. Gradually, several quiet voices begin to speak together. Then the cave becomes more than a hollow beneath the hills. It becomes a record of rain and rivers, changing water chemistry, ancient floods, vanished vegetation, passing animals, and human lives. Its messages rest within crystal bands, sheltered bones, grains of pollen, fragments of plants, and settled earth. The stream continues beside us, carrying new particles into the darkness. Perhaps some will settle here. Perhaps a thin mineral layer will eventually form above them. The cave's record is not finished. Even now, water and stone continue their patient exchange, adding another faint line to a manuscript that can be read only slowly, carefully, and with respect.